Speed round. K closest points to origin is a Phong staple because it quietly tests your grasp of heaps, quick select, and distance math without square roots. Tons of candidates sort everything in O(n) log n, and leave performance on the table. We'll solve it cleanly. With a heap you can code fast and a quick select outline you can mention for extra credit. Input: an array of points, x, y, and an integer k. We must return any k points closest to 0, 0 by Euclidean distance. Important: the actual distance sqrt x squared plus y squared is monotonic with the squared distance, so we compare xx plus yy to avoid sqrt. 3 main approaches. Full sort by squared distance O(n) log n, easy but not optimal. Heap, min heap, push all O(n) log n. Or better, max heap of size k keeping only the k best O(n) log k, and tiny memory. Quick select, /partition, to find the kth boundary in average O(n), then slice first k. We'll implement the max heap size k for speed and consistency. I'll also show a compact quick select. Plan with heap k. Define dist2p equals p0, p0, plus p1, p1. Maintain a max heap of minus dist2, point, or store, dist2, point, and invert logic. In Python we simulate max heap by pushing dist2, I, or dist2, x, y. For each point, push into heap. If heap size exceeds k, pop the farthest, the one with the most negative key because we stored negatives. Return the k points from the heap. Now let's solve solution 1 for the k closest points to the origin problem. This method uses a very simple approach: sort the points by distance. I'll walk you through the concept first, then explain every line of the code in a clean, easy way. Time complexity is O(n) log n, where n is the number of points. Sorting dominates the time cost. The idea of this solution: every point has a distance from the origin, 0, 0. Instead of calculating the actual distance, which requires a square root, we compare squared distance because it preserves the ordering. We sort all points by their squared distance, then simply take the first k points, the closest ones. Why squared distance? Because square root and squared values increase in the same order, so comparing squared values is faster and avoids unnecessary math. Line-by-line explanation of the code. Define a class called solution. Define a function k closest that takes a list of points and an integer k. Sort the points by their distance from the origin using x squared plus y squared. Return the first k points from the sorted list. And that's how this algorithm works. It first sorts all the points by squared distance, then returns the first k entries. Efficient, simple, and elegant. Sorting is the main operation, giving us O(n) log n. Complexity. We use squared distance to avoid computing square roots. This method is ideal when you need all points sorted by closeness, not just the kth distance threshold. It's very easy to implement compared to heap or quick select approaches. Now that we've implemented our solution to find the k closest points to the origin, let's check it with a real input. This helps us understand how the algorithm sorts the points by distance and selects the closest ones. We'll walk through the input, see how distances are compared, and verify that the output matches the expected result. Let's test the function using this input. The points represent coordinates on a 2D plane, and k equals 1, meaning we want the single closest point to the origin. Here's why the solution works. The algorithm calculates the squared distance of each point from the origin using x times x plus y times y. Then it sorts all points based on these distances. Finally, it returns the first k points from the sorted list. For this example, the point 1, 3 has a squared distance of 10. The point 2, 2 has a squared distance of 8. Since 8 is smaller than 10, the point 2, 2 is closer, and that is the one returned. And that is exactly what the program outputs, 2, 2. This confirms that the code is functioning correctly and passes this test case. So our implementation is correct. The algorithm successfully finds the k closest points to the origin. It correctly computes distances, sorts them, and returns the expected result. It works efficiently for this test case and scales well for larger inputs. This is solution 2. Finding the k closest points to the origin using a max heap. We maintain a heap of size k, always keeping the farthest point at the top so we can efficiently replace it when a closer point appears. Time complexity is O(n) log k, where n is the number of points. Heap operations are log k, and the heap never grows beyond size k. We import the heapecp module to use Python's built-in heap operations. We define a class solution to contain our function. The function k-closest returns the k-closest points to the origin from a list of points. Initialize an empty list to act as our max heap. For each point, calculate its squared distance to the origin. Squared distance avoids using square roots, which are slower. If the heap has fewer than k points, push the current point onto the heap. We use dist because Python's heap is a min heap by default, so negating the distance simulates a max heap. If the current point is closer than the farthest in the heap, replace the farthest point with this one. Finally, extract the coordinates from the heap and return them as a list. The heap never grows larger than k, so all push and replace operations are O log k. Squared distances are sufficient for comparison. This approach is efficient for large N because we only maintain k elements in memory. And that's how solution 2 works. It first initializes a max heap of size k, iterates through each point keeping the closest ones, and finally returns the heap contents. Efficient, clear, and practical. Before checking the output, let's understand the problem. We are given points equals 3, 3, 5, -1, 2, 4. A list of 2D points k equals 2, the number of points closest to the origin we need to find. The goal is to return the k points closest to 0, 0 based on Euclidean distance. Let's test our function with this input. Each point represents coordinates in 2D space, and we want the 2 points nearest to the origin. Here is why the solution works. Compute squared distances for each point from the origin. 3, 3, 3 squared plus 3 squared equals 18, 5. -1 5 squared plus -1 squared equals 26 2, 4 minus 2 squared plus 4 squared equals 20. Use a max heap of size k to keep the closest points, push points with negative distances to simulate a max heap. If a new point is closer than the farthest in the heap, replace it step by step with this input. Add 3, 3 heap equals 18, 3, 3 add 5, -1 heap equals 26, 5, -1 and 18, 3, 3 add 2, 4 distance equals 20 which is less than 26 replace 5. -1 heap now contains 3, 3 and 2, 4 the two closest points, and that is what the program outputs, 2, 4, 3, 3. The order may differ but the points themselves are correct. This confirms the code works correctly for this test case. Our implementation is correct. It successfully finds the k closest points to the origin. It correctly calculates distances from the origin. It efficiently keeps the k closest points using a max heap. It works for any list of points in 2D space. Breakdown recap. We're given n nodes forming a connected, acyclic graph, a tree. Our goal is to find all possible root nodes that produce the minimum height when the tree is rooted there. In simple terms, we're looking for the tree's centers, the points that minimize the longest path to any leaf. Assess recap. The brute force approach would be to run BFS or DFS from every node to measure height, but that's too slow. Instead, we realize that the tree's centers can be found by trimming leaves layer by layer, just like peeling an onion. Each round, we remove the outermost leaves until only 1 or 2 nodes remain, which are the centers of the tree. Structure recap. We handled small cases first. If there are 2 or fewer nodes, we just return all of them. Then we built an adjacency list and tracked the degree of each node. Next, we added all current leaves to a queue, and while more than 2 nodes remained, we kept removing those leaves, updating their neighbors, and collecting new ones as they appeared. The final remaining nodes are our centers. Implement recap. After coding this peeling logic, we ran it on LeetCode, and the solution executed smoothly without any errors. Check recap. We verified it across multiple test cases, and each time, the output correctly identified the minimum height tree roots. Closing insight. The big lesson? Sometimes, finding the center of a problem means working from the outside in. By trimming layer by layer, we let the structure reveal its own core, efficiently, cleanly, and in linear time.